Good afternoon. Welcome to Webinar Wednesday. We're excited to have over 270 registered attendees for today's webinar, which is eligible for 1 credit from the ACI. Let's get started by giving one lucky attendee a Webinar Wednesday lunch bag for answering this trivia question. Today's sponsor, Conquest Imaging, is headquartered in California. What is the official state tree of California? Answer now using the questions feature on your dashboard. While you're answering, I want to invite everyone to join us for our full MD Expo conference, which will bring HTM professionals from across the nation to Seattle from October the 5th to 7th for 3 days of learning, networking, and the latest advances in technology, products, and services. Registration is now open. More details can be found at mdexposhow.com/Seattle. Okay, and let's see who the winner of our Webinar Wednesday lunch bag is, and it is Jeff Grubb. Congratulations, Jeff. The correct answer is the Redwood. Webinar Wednesday would like to thank our sponsor, Conquest Imaging. Conquest Imaging is the largest supplier of ultrasound parts, probes, transducers, probe transducer repair, training, service, and free 24/7 technical support. For more information, visit conquestimaging.com. Our presenter today is Bob Broschart, Senior Director of Technical Operations at Conquest Imaging. Bob, you may begin whenever you are ready.
Thank you, Linda. Well, good afternoon, everyone. Thank you for joining today's webinar. And today we're going to talk about ultrasound probes and why do they cost so much money. And any of you in ultrasound, I'm sure you know what I'm speaking about. The range of pricing is very wide, but overall they're quite costly. So what I want to do today is kind of give you an idea of why they cost so much. We're going to talk a lot about how they're manufactured and a lot of the costs that go in. And I do want to say up front, I am not here to be a proponent for why they cost so much or a defender why they cost so much. It's just stating facts, and this is why all of us in the industry have to deal with these costs. And then we're going to kind of wrap it up a little bit with how we can protect that investment that you're making in your ultrasound probes. So if I can get there we go. So again, the agenda, we're just going to do a quick overview of the ultrasound probe assembly, a little bit about how probes are designed. I'm going to talk a fair amount on some of the raw materials that go into probes, testing, especially things like biocompatibility testing. We're also going to talk about array manufacturing, which is something I have some background in, and share some of the insights there. Electronics today. The electronics of the probes has increased in both cost as well as performance, and we're going to talk a little bit about that. Something I don't think a lot of people really understand is how these probe cables are made and designed and so on. So we're going to talk about that. Talk about some of the various materials that are used as well as where they go on the probe, such as plastics and some of the silicone materials and so on. Then how the final probe assembly is done and some of the labor involved, etc. And then just an overview of where the cost lies, mostly from the OEM's perspective, but why these things cost what they do. And then again, we'll kind of wrap it up on some basic things that you can do to protect that investment a little bit, and then we'll open it up to questions. So again, any of you that work in ultrasound, I mean, you know what you're looking at there. This is just a general standard imaging high-frequency probe from Philips. But it exemplifies really, I think, any ultrasound probe. Every probe's got connector, housing and block that connects to the ultrasound system. You've got some sort of locking mechanism. You've got your cable, which has a strain relief on both the connector end as well as the probe head end. You got your probe housing, and then you've got a probe lens, which covers your array. So from the outside, you kind of look at an ultrasound probe and say, well, it doesn't look like it's that complex of a device, when I hope to, by the end of this hour, show you that actually it is quite complex, and the costs that are involved in designing and manufacturing them is one of the reasons that they are so expensive. So basic design of an ultrasound probe, again, these are what I would call the major components, major sub-assemblies, if you will, of any ultrasound probe. Obviously, you've got an array, and the array itself is an assembly. So we'll touch a little bit on that, but that's got to be made. And the cable is an assembly with all sorts of individual components, not just wires involved in it. Obviously, electronics, you've got your circuit boards and the various components on those, as well as the interconnects that have to be on circuit boards to connect either to the array or the cable. You've got plastic, generally plastic housings and so on to enclose these items. You have plastics and metal in some cases to enclose the connectors. You've got all the individual pieces like strain reliefs and so on, locking objects, etc. Plus, you've got screws and bolts and nuts and everything else, as you do with anything to hold it together. So where do the OEMs kind of start with the design of a probe? Well, you know, for one, the probe, I think, and I know I've given talks on this before, but the probe really is what I consider the heart of the ultrasound system. It's the one that's receiving data back from the patient, and the system is forming that into the images that we see, Doppler, etc. And it really begins right there, because if we input bad data, the machine is just going to put out whatever it sees. And that's why I think so much engineering effort and R&D is put into the probe by the various OEMs, because it really starts with that. And the system is there to support the probe, in my opinion. You know, one of the things, and I think it's especially true in the last 10 years at least, if not longer, is that design engineers are really spending a lot of time on image quality improvements, image enhancements, and that starts with the probe. And it's really about not just improving that image quality, or maybe even the Doppler. There's some new technologies out in Doppler that are quite good, but it's all about how can they improve the diagnosis of disease using ultrasound. It does also, I'll speak a little later on this, again, ultrasound, because of these design efforts and engineering, have been able to expand into clinical areas that even 10 years ago you couldn't use ultrasound in. And that continues. I see that continuously happening, and it's really exciting if you're in ultrasound, I think, to see all the various clinical adaptations that ultrasound has moved into and can be used in now. Obviously, the array is the key, as I mentioned, so that's got to be designed, and it's got to be tested and proven and so on. Electronics have to be put in to operate that array and connect to the system and so on. You've got transmit and receive signals that have to be processed through the probe, so all those electronics have to be created as well. Again, various plastics and silicone materials and adhesives and so on all go into the design of an ultrasound probe, and every one of them has to be looked at. You can't leave anything out. Cable design is a completely different project. Again, it's got to be able to fit and connect to the interconnect on the array. Sometimes that's done by individually soldering every microcoax wire onto the array. Sometimes it's done with flex circuits, and sometimes it's micro connectors and things like that. It's various things. It just depends on what's the engineers come up with to optimize their design. And they've got the cable has to work electrically, but also make sure that acoustically it's not got a lot of noise, signal noise problems, or signal loss. So those things all have to be factored in. Not to pick on the cable, but the actual diameter of the microcoax varies in these ultrasound probes depending on the array and the frequency the array is operating at. And a lot of that is due to signal loss or noise. One of the things I think, and we'll touch more, but a lot of people tend to think the lens on most ultrasound probes, and it is, I will tell you, a lot of them are just a base silicone material. It's a compound, but that's got to be designed. They're looking for the optimum acoustic output, or throughput even, if you want to say that, of the lens. Again, you don't want signal loss and things like that. So believe it or not, there's a lot of design work goes into the lens, and there's ways I'll show you that they test for that. One of the things, and we all know it, you can't run down to Fry's Electronics or something like that and buy an ultrasound probe. And that everything's got specialized tooling. I've been on the manufacturing end myself, and I've been on the repair end, and I am in the repair end now. And every tool you have, you've got to develop. They just don't; those aren't off the shelf either. So to make the probes, manufacture the probes, to repair probes, you've got to have specialized tooling, and that just adds cost. And one of the things with probes, it's got to be designed, anything in manufacturing has to be designed so that it's manufacturing friendly. It's got to be repeatable, your processes have to be consistent, and you want to keep the cost as low as you can, because again, these things are going to be expensive enough for the OEMs just through materials and some of their other costs. So talk a little bit about raw materials. Again, in the upper left-hand corner there, you see these are just some of the various crystal-type materials that make up most piezoelectric arrays, PZT arrays, just various raw earth materials that they use to manufacture the actual array crystal. You've got your raw plastics, which typically come in a pellet form like that. And you've got to make sure that's medical grade plastics. You've got silicone materials, again, for lenses or any strain release, other rubber pieces. With the cabling, you've got your raw cable, your microcoax, which has bundles anywhere from 64 to 256 wires. You've got a PVC type of material that encloses the cable jacket. And then you've got a wide variety of adhesives and sealants. And all these things really need to be medical grade. And again, that adds cost. I'll talk a bit more on that later. So looking at the materials used, material testing, biocompatibility. Well, all materials that are going into an ultrasound probe really need to be medical grade, and you need to do a biocompatibility testing on to make sure that they are biocompatible. I just put in a little clause here by the ISO, International Organization of Standards, as many of you are familiar with. But the primary aim of 10993 is to protect humans from potential biological risk arising from the use of medical devices. And, it really has to do with the third bullet point there kind of touches on it. Ultrasound tests are usually cytotoxicity, sensitization, and irritation. The last thing you would want to do, for instance, is design a probe, use some sort of non-medical grade or biocompatible material for the lens so that every time it touches someone, they get a skin rash or irritation. And while we may not think about those things every day, obviously, it is something that you have to consider. So testing these for biocompatibility use making sure your materials are of a medical grade. And that goes right down to the fourth bullet point there. Even your adhesives and your plastics, and I mentioned the silicone rubber materials, everything needs to be of a medical grade, and you want to have the items biocompatible tested. And the one thing you want to do is and the manufacturers have to do this, is once they complete their probe assembly, it gets it tested for biocompatibility as a whole, so that the various materials and maybe any chemicals that were used in the manufacturing process and so on do not turn this into a device that fails biocompatibility testing and could be harmful or cause some sort of irritation and so on to the patient. You know, one of the things that I know you're all aware of, and happened several years ago now, but you know, had to do with the gloves, and find out people with allergies to latex. You know, years and years ago, a lot of hospital gloves were just latex. Well, it started causing problems. So these things have to be tested, and it's a good thing that they've done. But as I'll say probably on every slide here, this adds cost. I mentioned earlier a little bit about the lens testing. Again, I don't think a lot of people realize what goes into just making the lens. Obviously, we all see it on the probe. It's one thing. It's what touches the patient, etc. But the actual design of those is a lot more complicated and a lot more detailed, I think, than you think. Even again, I'll say even from a repair standpoint, we go through a lot of testing and validation just to replace a lens, because we got to make sure it's, again, biocompatible, if it is not changing the acoustic output. So when you are on the array design side and you're designing this array, well, if you put a crappy lens on there, you may have the world's greatest array that you could just put on somebody's head and scan their entire body, but if the lens is bad, it essentially becomes worthless. So the OEMs, they have got to make sure that they're, again, using the right material, the shape, the thickness is critical, and they've got to run tests on this to see that when they're sending a transmit signal out through the lens, through the array, through the lens, and then receiving that back, how's it attenuating out? Is there a lot of signal loss? Is it scattering? You know, one of the things that we've seen over the last several years, certain probes of Philips, GE, Siemens, all three specifically do it. They've got lenses with various metals in them. We've seen gold, silver, aluminum, and all these things are done based on the arrays they're using on these particular models, certain models, to improve the image performance, but also to make sure that they're focusing their beam properly, reducing noise, etc. So there's a lot of testing goes into these lenses. But again, this adds significant cost. You need a special device to do the lens testing, and then all your standard design work as well. So the array. Again, the array itself, and some of you may have seen this before, but you've got several different pieces of the array. You've got, again, your lens, matching layer, backing layer, the element itself, etc. So all these things go into the design of an acoustic stack, as we call it. I mentioned it earlier, probably can't emphasize it enough, but one of the big costs for the manufacturers is the array. It's going to be critical to the performance, obviously, of the probe, and it's also going to contain a lot of the cost, if not the bulk of the cost. R&D engineers continue to design arrays that, like I said earlier, expand the application of ultrasound and increase that clinical performance. and it's continuing to move at lightning speed, in my opinion. But it all starts there. Design and manufacturing of arrays is costly. There's a lot of design time, especially from scratch. Material costs can be high. As I show here in bullet point 4, raw crystal material, raw earth for crystal material is very costly. Right now it's over $1 million a cubic ton for this. So again, you can see that just the cost of the raw material alone is very high, and that all gets passed down to us who have to buy these. Manufacturing process is certainly not easy in arrays as well. I've been fortunate to be at a few manufacturing facilities of arrays and see it. It can be long lead times on it. One of the big things I think that a lot of folks don't realize is that you don't go through a array manufacturing process and you build all these arrays and you build 1,000 arrays and you put 1,000 arrays through the manufacturing process and you get 1,000 out at the end. They're actually can be low yield. And this one that I put in here is with the single crystal array types that are more and more popular today, are in a lot of probes, give tremendously good image quality, but the manufacturing yield on those is just barely over 50%. So they're losing, half of everything they input, and ultimately that just all gets passed on to us. It drives up the cost of the array, but those costs get transferred on to us. And you can kind of see the process there. They've got to put the materials in, mix it together. They do some molding, getting the array set up. It's heated, and I'll show that in a second. Shaped. They've got to what they call polarize the arrays, and then age them. But the process looks simple, but again, every step of this needs special tooling. So one of the things that is done, arrays go under very high temperature, several thousand degrees Fahrenheit, and the materials come in, the blocks come in, and it comes out at the end. And there's things in the upper right-hand corner of this picture is of basically a small, I'll put it in layman's terms, it's like a bandsaw, but it has to cut the grooves in the array. It's called splintering. And again, that's not something you're going to find at the local hardware store, So they're very specialized tools. These ovens and so on are very specialized, very, very costly. So for the manufacturers, again, if you think through the loss they have with the arrays, just in the manufacturing process, plus the fact that they've got all this expensive tooling and so on, you can see where these costs start to add up. So they've got to make a lot of these to also even make it feasible for themselves. And again, they're just talking about the yield loss. All these things add up to the point where some of these arrays are quite expensive, and again, it just gets passed down to us who have to deal with purchasing these. Now, one of the things that you may or may not be aware of, but again, this is a cost, and this is an expensive cost, is once an array is designed and finalized and manufactured, well, one of the final things the OEM has to do is get it acoustic power tested. There is a requirement by the FDA that, and I attached the chart right out of the FDA guidelines, that depending on what the array is used for, vascular, cardiac, fetal, which includes abdominal and so on, these acoustic output levels are set for the FDA by the American Institute of Ultrasound and Medicine and others. And as long as the OEM's new array meets these levels, that's fine, but they can't exceed them. So guess what happens? If they design an array, let's say a vascular array for use in vascular imaging, and it exceeds 720 milliwatts per centimeter squared, they have to go back to the drawing board and figure out, okay, well, now we got to do a redesign, rework to get that down below that level. That is the one thing that the FDA is very stringent on, is power output for arrays. So again, the OEMs have to do this. It's required. I personally think it's a good thing. And, you know, they've got to make sure it's going to be safe. But I can tell you this cost is in the thousands and thousands of dollars to do these power tests. And it's just another thing that gets added to the equation with the final cost. So talk a little bit about electronics. Again, it's just another cost factor. You know, I see more and more probes today, and the new ones coming out, that more and more the probe electronics are actually in the probe head, as well as in the connector where they've been for years. And again, that's all due to working with these new array types and how you want your clinical performance to be, et cetera. So again, every stitch of that has to be designed, the board flat, the component circuitry, et cetera. More and more probes, I talked about this in other sessions, are multiplexed. A lot of them are using CPLDs, complex programmable logic devices, VGA chips, et cetera. Some of these components are very costly, even if they're using off-the-shelf components. Granted, the manufacturers, when they build thousands of probes, they get a price break off of you or I trying to buy one or two, but they're still costly. And again, they're designed into the probes to maximize the performance of the probe, which is wonderful, but it adds a cost. Now, the multiplexing is a big one, but these have to be designed. You know, it has allowed probes to be able to simulate thousands of elements as opposed to, you know, 128 elements of old, things like that, which certainly does help with the clinical performance. But again, it's got to be designed. The circuits have to be designed based on how you want the array to send, receive, what clinical application it's used in, etc. So all this again is just putting more cost into the device. Now, today I mentioned a little bit earlier, you know, a lot of probes nowadays are what we call matrix array technology. And these are all multiplex. They all use components like CPLD, etc. Some of them have firmware in them. There's flash, if software flashed on the components, etc. So again, you stop and think about it. If you've got to flash a component, for instance, put some software on it. So you've got a software developer involved to create the software. Then you're working with an electronics engineer to make sure that they've got the right component. They've got to design the process to get that flashed in, both from a manufacturing standpoint as well as the initial design. Then there's the issue of how does it mount to the board, et cetera, et cetera. So there's just several levels, even on the electronics, that you have to go through to make these things work properly. Now, one of the big things today is that's used in several probes in the market, especially 3D, 4D, TE, is what we call ASIC. And any of you that have used the Philips X72T TE probe have probably heard that term a lot. This is just the Wikipedia definition of it, but an ASIC is an application-specific integrated circuit. And what it does is it's a chip that is designed specifically to do a function for a device. And these are used obviously in things other than medical, but you know, you can see where, like example that Wikipedia uses a Bitcoin miner. They had to create an ASIC because they needed that miner to do a specific task, so they need a chip to tell it to do that. Whereas you've got standard off-the-shelf components, and I know I'm quite familiar with the 7400 series, 4000 series components. Those are off-the-shelf things. They're not expensive, but using an ASIC is. It is increasing in the use of ultrasound, and it's been very successful. Philips has been very successful with it. GE and Siemens are using them. And again, it was done to increase that clinical performance, clinical applications, and so on of the ultrasound probe. One of the things I think that a lot of people don't know, though, is that just the development cost for one single ASIC component can run you close to $500,000. So if you stop and think about it, the manufacturers spend $500,000 to do one. What if they say, well, okay, we need another one in that probe that's going to do something different? So you can see the upfront development cost, you know, can run in the millions. So again, that cost has to go somewhere. Where does it go? Well, it goes into the end product and out of our pocketbooks. I mentioned the example, and the best examples, I think, of ASICs today is in the some of the 3D, 4D TE probes that are being used. What's kind of unique is the ASICs in these situations, the engineers have designed them right in with the array assembly. So they've created an assembly that it does make it difficult to repair, I can tell you that, and even diagnose what's going on. Because it's very hard to determine, okay, has the ASIC failed? Or has the array failed? Both? Neither? It's very difficult. But again, you can see that they've made good use of this technology, and again, it's really helped with the clinical performance of the products. It is costly, though. These probes, probably don't need to tell you if you use them, are very costly. And a lot of that just has to do with the basic design and the ASIC. So we'll talk a little bit about cables. Again, cabling is a thing. You can't just go off the shelf and buy a microcoax probe cable. It doesn't exist. It's a very tedious process. You've got to go point to point, even in the cable design, from the connector boards and connector block to the array. So you've got to know which wires go where. All that has to be diagrammed out. So you have your wiring diagram, and then you've got to start your assembly. So one of the other things is, and this unfortunately does add cost to the probe and increases its price to us, is that microcoax wiring is only made by a very small number of manufacturers, and it's worldwide. It's a very specific cable. I mean, it's a standard coax, as you can see in the lower picture there. It's got a center conductor, which is insulated. Then you've got a ground shield, and then your outer jacket. But this isn't like your cable television coax. It is, but it's the size of, you know, human hair, a little better in some cases. So it's very small. Because of the limited number of manufacturers, that increases the cost of the raw cable. And the raw cable is really the key component. That's got to be manufactured correctly. And the biggest thing is because of what it's used in ultrasound. You know, you're talking about a small coax wire that has to transmit at a high voltage signal to transmit the ultrasound beam out. And then it's got to receive back very low amplitude RF signals, and it's got to do this while maintaining a very low signal to noise ratio, a clean signal, and not causing a lot of problems. You know, if you don't design, for instance, if you're the cable designer working with the ultrasound OEM, if that insulation on the center conductor is not right, if you don't have them connected right on the ends or something, and you start getting crosstalk between wires, what you're going to end up with is a very noisy looking image, which is obviously the last thing in the world you want to do. And you got to pay great attention to things like crosstalk and so on. Again, I've been fortunate to see these made, and the way they bundle the wires within that outer PVC jacket is an art in of itself. And a lot of that is done to reduce signal to noise ratios and make sure there's not any problems with crosstalk. A lot of steps go into a cable. I've done that, and first time I was involved in it, even I was amazed at how much work has to go into designing a probe cable. Obviously, you got your raw cable. You got to figure out your connectors. You got your system end connector, which is going to be based on either off-the-shelf or a special design connector. But you're going to have circuit boards in some cases, flex circuits, things like that. Micro connectors on the end of the wire if you want it to plug into an array, or is it going to terminate by soldering the wires, as I mentioned earlier. You got a strain relief at the connector end. You got a strain relief up where the cable is going to plug into the probe head. So that's got to be designed. That's got to be manufactured. You've got to have RF shielding in there, again, in addition to just the outer shield of the microcoax. Outer jack material in many cases is PVC, but sometimes it's not. You know, what is it going to be? And then you've got all kinds of little hardware, again, screws and nuts and bolts and blah, blah, blah. All those little things that are put in there. Ferrite coils go into a lot of probe cables to help with EMI. So, again, everything they do adds a cost. Cable manufacturing is another unique thing. Probe cable assemblies are handmade, and I'll talk more about that when I get to the probe assembly, but you know, it's hard to believe in today's world of automation, but they're still handmade. You know, the wires have to be cut, prepped, stripped, and most of the time that's done by a laser. Again, and lasers are not cheap. They've got to do testing, and cable manufacturers I know of do 100% testing, high pot testing, conductivity testing to make sure that cable's good. You've got bar soldering, hand soldering, wires, etc. And I mentioned you have to create tooling and molds for the strain release and other rubber or plastic parts that go into that probe cable. And those all require specialized tooling and so on. So again, it just adds cost upon cost. Plastics, fairly straightforward. Again, probes use a variety of plastics. The outer housings, even nose pieces, domes, handles for the locking mechanisms, etc. Now, one of the things, again, the plastic materials need to be of the medical grade. They need to be biocompatible. One of the things that the manufacturers know, and I know from a repair standpoint, is that these materials, as soon as you say medical grade to a materials manufacturer or supplier, their eyes light up because the price goes way up. And they're much more expensive than standard plastic. But again, we all know what the industry we're in, what we're using them for. So, but again, it just adds a cost. You know, everything in that plastic housing that you see there has to have CAD work done. It has to be designed. You're going to have to create tools to mold this for injection molding, etc. One of the things that adds cost to the OEMs is any time that marketing or sales, whoever's driving the development, from that perspective says, well, we want some improved ergonomics and comfort. We want it to look this way or that way. And just looking at this this GE probe, those ridges in the handle, in the white part of the handle, that adds cost like you wouldn't believe to the tool, because the tooler has to make the tool to do injection molding for that housing, and those ridges and so on add, again, significant cost. And then you turn around, as GE has done in this case, and they wanted a blue nose piece. Well, as soon as you add colorant, that adds another cost. And again, this just keeps adding up to what we end up paying for on the end user side. Again, if you're not familiar with injection molding, you feed the raw material in, material's heated, and then it flows into your mold tool there in the center. Again, the tooling mold all has to be designed. Then you have to look at flow patterns and so on. There's some analysis you can do there to make sure that the material is going to flow right when it's in the injection machine. And just like arrays, again, I've been fortunate to see this and do this. You do not get 100% throughput on a plastic housing. And matter of fact, sometimes depending if your tool's bad, you can get a significant loss. And I've seen this done with probe housings, and I've seen the guy stand there at the machine, and they come down, he looks, throws one in the trash box, and the other one goes onto the good belt, if you will. And again, every one of those that gets thrown away is still a cost to us on the probe side. Connectors. Every probe's got to connect the ultrasound machine, obviously. Some of these are more specially designed nowadays, but there's still a lot of off-the-shelf connectors that some of the big connector companies manufacture as off-the-shelf stuff. And it's always better from a cost perspective if an OEM can use off-the-shelf stuff, but sometimes they can't. You know, again, they've got to look at it and say, okay, I've got a cable. I got to make sure it's going to fit the cable. I got to make sure it's going to fit on the system connector and the array, etc. So there's a lot of engineering work that has to go into that as well. Again, just a little shot here, kind of an open connector. You know, one of the things that adds cost really in this area, but it's throughout, I think, the whole process of probe manufacturing is, you know, you're going to have a team that's developing the connector and maybe the electronics. You're going to have another team that's developing the housing, connector housing, for instance, that goes around that probe connector. Well, they've got to coordinate efforts, obviously, and share data and share drawings and so on and so forth. Again, the more this is done, the more costly it is. Then you've got to design a locking mechanism. You've got to have it lock into the ultrasound system somehow, right? So that's got to be designed. That's going to have plastic parts and generally a metal connecting rod and pins and clamps and so on and so forth. So every little thing in there has to be thought through, designed, and put into the process. Again, rubber components. So you've got rubber, silicone lenses, like I mentioned earlier, strain reliefs. When you get into 3D, 4D probes, you've got oil bladders and other rubber silicone materials that are used in the manufacture of those probes, and they have to be designed in. Insertion tubes for transesophageal probes have a silicone material, and so on. All those have to be designed, tooling made, molds, etc. And again, it just adds cost. Tooling in rubber for ultrasound probes, it can go from the very basic to a 3D printed mold to some very complex stuff. Again, it depends on what the engineers design into the probe. Again, insertion tubes are a little more complex, so they're going to have specialized tooling. Again, there's just a few companies that manufacture these. That drives up cost. It just depends on how complex things are designed at the engineering level. So the final assembly of probes, which is another cost thing. Once you've got all your parts designed and tested and so on, well, then you put them into manufacturing. So now you've got to make the sub-assemblies first. And every one of these sub-assemblies has to be tested through the manufacturing process. So we've discussed the array a little bit. So those have to be tested, your cables, all your electronics, you've got your connectors. When you get into 3D, 4D, and TE probes, you've got a lot of mechanical parts and other things too that go into the assembly piece of it. Again, in today's manufacturing world, a lot of us, we see it in the news, etc. We think of manufacturing as all these automated robotic systems manufacturing automobiles and other things. I can tell you emphatically that in the world of ultrasound probe manufacturing, they're still handmade. And you'll go into some of the big probe manufacturers, and there'll be hundreds of people sitting there building these probes one at a time. And there's some reasons for that, obviously, but it includes, I mentioned earlier, the cables are handmade. There might be some automation a little bit on the PCBs, at least with soldering and so on, but the arrays have to be handmade, but the final product is really put together by hand. They'll have some tools and so on, but since you're using people, and people are generally our highest cost with anything we do, that adds a lot of labor cost and price to the final product. The other problem that you have in probe assembly and manufacturing is that with anybody, anytime any of us as human beings do anything, we can make a mistake. So there's rework. The rework might be the material was bad. You got a bad lot of housings or something, a bad lot of material. But then you have your workmanship issues. Something didn't fit right, but you pushed it through. So all those reworks have to be done. And again, drop out. If there's a manufacturing loss, you drop it out. So that adds cost. So overall, I think, and hopefully I've been able to show you a little bit, that an ultrasound probe assembly really is kind of a complex beast. It's not as simple as the first slide I showed with just the external pieces. There's a lot that goes inside those pieces. Obviously, with a lot of things, especially technical products, a lot of the cost is in the IP or intellectual property. And the manufacturers have the right to charge for that. How they price that is they have to go through and recuperate their engineering costs. It includes all their engineers' time and so on and so forth. So that's going to factor into the cost. Material costs, especially arrays, can be high. And you get the power testing. The labor to assemble, like I said, is very costly. And then, again, looking at manufacturing costs such as yield losses and rework and things like that. That adds up pretty quickly. As soon as you start getting into TEE, 3D, 4D probes, that just adds a whole nother level of complexity. You've got mechanical parts, you've got liquid mediums, motors, drive cables, things like that. That all adds not only to the design cost, but also the manufacturing costs of these. And the bottom line is the more complex the probe is, the more it's going to cost us. And these new technologies do tend to be more expensive. And again, I mean, let's face it, there's a market value that I know the manufacturers try to put on probes and other devices. How they calculate that varies, but you know, I do know when someone rolls out a new technology, they're going to try to get top dollar for it. But there is a cost behind it to an extent as well. So what's the best we can do? And I'm not going to blow you away here with anything that's super new, but I am going to say that I've said this. I've had other colleagues, other companies in the industry been saying this for years, and honestly, I still don't see it happen like it should, but there are ways you can protect your probes. And a lot of it's just basic. When you're doing a preventive maintenance check, you got to look at every probe, and you've got to do a very good physical examination. You know, make sure they're working. Ask the sonographers if there's any problems. But it's really about catching these problems beforehand. Again, looking at the, you know, physical issues, like I said, you know, pinholes and leaks and so on and so forth. Make sure that any probes going through high-level disinfection are being disinfected properly and are not, you know, especially TEs, you don't have bite marks and you're flooding the probe out and so on. You really need to do an electrical leakage test on your probes at every PM. TE probes are supposed to be done after every patient now. It's a requirement. And, you know, they really should be done even on the PMs. And check your cables again. Move it around, put it in Doppler or color Doppler and see if you get any flashing and so on and so forth. The key is, because these probes are so expensive, and I just can't stress it enough, you've got to take a few minutes and really inspect them well. Get yourself a magnifying glass and look at that lens under a magnifying glass and look up and down the insertion tube on a TE probe and others, because if you can catch it up front, it's going to protect you in the long run. You know, again, waiting till a problem gets worse, and it makes me cringe, is I've had people tell me, well, I know I've got a hole here in this lens, but I think I'll wait until it gets worse. Well, as soon as you do that, the problem's not going to get better. It is going to get worse. Problem is, so's the problem itself is going to get worse, because you might get fluid or something else down in there and destroy your array. Now you went from a, you know, few $100 repair to thousands of dollars of a possible replacement of the whole probe. So that just doesn't make sense to me. You're going to save money in the long run and protect that probe investment by handling it up front. You know, I've had people ask me repeatedly still, well, how long should a probe last? Well, you know what? It's going to last forever if you take care of it. Now, you're always going to have things fail. It's an electronic device. You can't predict that. But, you know, trying to catch these things beforehand, you know, I think if you don't take care of them by monitoring them, working with your customers, again, at the sonographer end and so on, department managers, if you don't do that, you're just adding to the problem. And you don't want to do that. You want to get these things caught beforehand, because I can tell you the economic impact is huge. You can't necessarily control to the extent when probes are going to fail on their own, but you can protect and predict those that are being misused in some sort. Again, misdisinfection on or improper disinfection on TE probes is the #1 reason we see TE probes come in for repair. And that can be prevented. That is preventable. And again, you just don't want to add to the overall cost for your department, for your hospital, by adding to it by not properly evaluating these probes and maintaining them. Because the one thing we can all be assured of is that the costs are going to continue to go higher on ultrasound probes as these new technologies come out. And the more complex probes that come on the market, the more they're going to cost. And not only is it that, again, I'll speak from my perspective on the repair end, the manufacturer's got selling a probe with a high cost because of their manufacturing costs. You can rest assured that the repair costs are going to be higher for those too, because it just goes hand in hand. Not that we want them to be higher, it just is because we have to have special tooling, blah, blah, blah. And again, if we can protect those from failing in the first place, that's much better. And that kind of sums it up for me. I thank you again for attending, and if there's any questions I can answer, I'd be happy to answer them, or you can email me at bbroschart@conquestimaging.com. I'd be happy to answer anything.
Great, thank you so much, Bob. Yes, we have got a couple of questions we've got time for. The first question is, what would you consider the most important aspect of probe repair price?
Well, probably the most important piece of the actual sorry, Linda, tell me the question again.
So it's, what would you consider the most important aspect of probe repair price? Sorry.
Probe repair price. Yeah, I think the biggest thing on probe repair cost is when we get into the arrays. Anybody repairing probes knows that just as I said in my presentation, the manufacturers have the highest cost of the probes really in the array. The exact same thing is true on the repair side, and kind of goes hand in hand with what I was wrapping up with in protecting your probes. Is if we can keep the arrays from damage and keep them working, it's going to reduce your repair cost.
Okay, that's great. Another question is, what is the one thing that I can share with the other people in my department that will help us save on our overall probe repair spend?
Well, I think the biggest thing that I would recommend is catching these problems early. I hear a lot of, well, okay, if I send a lot of probes in for these minor repairs, I'm going to be spending a lot of money, but in the long run, you won't. And there's been enough facilities I've worked with that have done it that way and actually seen their spend go down because they're not spending as much and they're keeping their probes in good working order. So, I know I've seen places that would send 10 probes a month in to get lenses and some of the other minor repairs done, as opposed to sending in 2 a month that cost them thousands of dollars because the array's been damaged. So I think that's probably the one thing, is to catch these problems early, and let's take care of it for you right then.
Okay, well, we've got time for one more. Do you have a procedure for completing an electrical safety test on the probe?
Yes, we do. If you want one, just email me and I will be happy to send it to you.
Okay, that's great. Okay, well, we've come up to our hour, so thank you so much, Bob, for a great and very informative webinar, and thank you again to today's sponsors, Conquest Imaging. One lucky attendee will win an Amazon gift card for completing the post-webinar survey, which will appear on your screen shortly. You must complete the survey to obtain your certificate of attendance. For more information about our upcoming webinars, please visit our website, webinarwednesday.live. Thank you once again for all attending and enjoy the rest of your day. Thank you.